In a world filled with math, they learned about logistic functions and their graphs.
The parent function for all logistic functions is f of x equals 1 divided by 1 plus e to the negative x. The horizontal asymptotes for the parent function is y equals 0 and y equals 1. The horizontal asymptotes for a logistic function is the numerator for the equation and y equals 0. Y equals 0 will always be one of the horizontal asymptotes. The graph will never reach the horizontal asymptotes, but will slowly approach it. The y-intercept for the parent function is y equals 1/2. To find the y-intercept for a logistic equation, substitute 0 for x and then solve the whole equation for y. There are two ways to graph a logistic equation. One method is to substitute any given value for x and solve for y, and use the x and y coordinates to plot points on the graph. However, this method will include multiple estimations and the graph may not be accurate. The second method is to use a graphing calculator to graph the equation. In order to draw the most accurate graph, sketch the horizontal asymptotes and the y-intercept, along with a few coordinate points. Then sketch the graph, passing through these points and approaching the horizontal asymptotes but never reaching it, to graph the most accurate graph.
This example can be found on page 262. It is number 41. It reads, f of x equals 12 over 1 plus 2 times 0.8 raised to the x power. Has the horizontal asymptotes of y equals 0 and y equals 12. The asymptotes are always y equals 0, and the numerator in this case, y equals 12. The y-intercept is found by solving for y when x equals 0. In the case of this example, it is x equals 0, y equals 4. As was said earlier, there are two ways to graph this: by hand, which includes a lot of estimations, and by using the grapher, which is what is done here. Type in the equation. Be sure to put parentheses when necessary. Then plot your asymptotes to get a good idea of how the graph is going to react outside of the screen.
Exponential functions are commonly used to predict population growths. However, instead of being f of x, they are p of t. In this example, p is equal to the population in millions, and t is equal to the years since 1800. This example is p of t is equal to 19.875 over 1 plus 57.993 e to the negative 0.035005t. For this example, we are told to find three things. A, the population of New York State in 1850. B, the population of the state in 2015. And C, the limit to growth. First, graph the equation. We recommend using a graphing calculator, especially for this problem, since there is going to be multiple estimations. After typing in the equation, set the window to where you can see 50 and 115, as those are t, which represent the years after 1800. 50 being 1850 and 115 representing 2015. Then you can go ahead and graph x equals 50 and x equals 115. Now for A. To find the population of New York in 1850, look at where x equals 50 intercepts with the graph. For this problem, x equals 50 intercepts the graph at 1.795. However, since this is population in millions, it would not be 1.795. It would be 1,795,000. Now, going back to the graph, look at where x equals 115 intercepts with the function. This happens at 19.273. However, since we know that the population is in millions, we can estimate that the population of New York State in 2015 will be 19,273,000. Now, for Part C, refer back to your graph. Look at where the top horizontal asymptote is. Here, we see that that is at 19.875. So, we can estimate that the maximum sustainable population, or the limit to growth, is 19,875,000.